Now, for tonight, we have Zach Meisel, an assistant professor in physics and astronomy, talking about life after death, element creation in stellar explosions. Enjoy.
Okay, greetings everybody. Thanks for coming out. So just so you know, this talk is going to be about nuclear astrophysics. So in case you thought life after death meant I was going to talk about something like reincarnation, that's not the talk, okay? So now's your time to get out and leave. So nuclear astrophysics, I just want to quickly tell you what it's all about and who does it, just so you get an idea of what it is that we do. So I'm an experimental nuclear astrophysicist, and what that means is that over in the Edwards Accelerator Lab, about 100 yards, I guess, that way, I do nuclear physics experiments that we're going to talk about a little bit to try to study stars, stellar explosions, the universe in general. All right. So nuclear astrophysics, though, really is a team effort. So we have astronomical observers. So these are people who point their telescopes at space. They tell us that these interesting phenomena are happening in the universe. All right. Then we have astrophysics theorists. These people say, hey, I think I know how to model that funny thing that we saw in space, right? I know how to reproduce that on my computer. But these astrophysics theorists, they oftentimes need nuclear physics input, right? So we have nuclear theorists and nuclear experimentalists, such as myself. We try to make sure that we know what the important input is to give to the astrophysics theorists. They run their calculations, try to reproduce the observations, and then hopefully we gain some understanding about the universe. So that's the big picture overall, and I'll try to work through that as we work through this discussion. So as a team, what we try to answer are really simple questions. So for instance, why is this barn red? Is anybody brave enough? Why is the barn red? Anybody? It's painted red, but why would you pick red? This farmer could have picked blue, they could have picked yellow, but if you drive around the countryside here, a lot of them are red. So why would you pick red? You're an economical, hardworking farmer, right? You're practical minded. Anybody? It's cheap, right? The paint is cheap. Thank you, yeah. Okay, we're getting somewhere. So believe it or not, this is connected to nuclear physics. We're getting there, okay? Okay, so why would red paint be cheap? Is it? It's because of the iron, right? So red paint is made with iron pigment, right? And iron is cheap, right? Okay, so now why is iron cheap? I'm not going to make you answer this one. It's because there's a lot of it laying around. Okay, so if you were to look at what the Earth's outer layers are made of, or really what the universe is made of, you'd find that there is a lot of iron laying around. Okay, so this is the periodic table, which you may remember from chemistry class or chemistry in college, or maybe you're a chemist. In case you haven't seen it, each of these boxes is a different chemical element, right? And the column tells you about the chemistry of that element. But then what's cool about this periodic table is that the size of the box tells you how much of this stuff we have on the surface of the Earth. Okay? So it's probably good that there's a lot of oxygen. You wouldn't be able to breathe if that weren't the case, right? So good, we have a lot of that. And then what you'll notice, though, is there's also a lot of iron, right? So one question that we try to answer with nuclear astrophysics research is, well, why is that? Why did the universe make so much iron, or so much oxygen, so much iron, but it didn't really make as much rhenium, right? It didn't make as much gold. Okay, there's a lot less gold, so why is that? And we can discuss why that is or how we try to figure that out. Okay, so while we're on the topic of gold, where did gold come from, right? So we're asking and answering simple questions here. So one question is just, where did this thing come from? So one clue, you might just try to read the writing. Let's just try to cheat, right? There's notes on there. So it turns out what that says is, I am the badge of Phanes, which doesn't help us very much, okay? So what this coin is it's the oldest known coin, or oldest coin known to humankind, and it's called a stater of Phanes, and that's pretty much all we know about it. It's from Roman times. We don't know if Phanes was a king or a people, or a queen for that matter. We have no idea, okay? But what we do know is that this stater of Phanes is made of this pretty cool old material called electrum, okay? And it turns out electrum is mostly made of silver, gold, and then some other mixture of stuff, whatever somebody doped it with to try to make more coins, right? Okay. So what we want to answer is, where did this gold come from, right? Civilization has been fascinated with it for a long time, and I think it's an interesting question. So is anybody brave enough? Where does gold come from?
We just saw in the news when two neutron stars collide.
Exactly, yeah. So I was going to make a joke and say rainbows, but we just killed that joke. So, but thank you. Exactly. It comes from neutron star mergers, right? At least that's one place. So there could be exploding stars as well. But recently what we saw in the news is that it comes from these two objects colliding, and they probably produce a lot of gold. And our very own Ryan Chornock, an assistant professor in physics and astronomy, was instrumental in proving that, which is pretty cool. Okay, so what these things are is you have these funny spheres here that we call a neutron star, and what it is it's an object that is the mass of the sun. That's pretty massive, but it's the size of Athens proper, right? It's tiny. This is an extremely dense object. So imagine compressing the entire sun down just into Athens, and you get one of these guys, okay, one of these neutron stars. And then it turns out oftentimes they wind up being in a so-called binary companion with a friend. They wind up orbiting each other. As they're orbiting each other, as you know from the news and as we'll see in a moment, they emit these things called gravitational waves that releases energy, and so then they spiral inward. And what this diagram is trying to show here is the temperature is indicated by the color, and you'll see that when these things merge, they get really darn hot, and they're already pretty dense, as you know. And what happens when you get really hot and dense environments, you have something that's kind of like a nuclear reactor, basically, right? It's so hot, you can break apart atomic nuclei, fuse them together to make new stuff. Okay, so that's pretty cool. So just while we're at it, let's actually listen to this neutron star merger. This is sort of fun. So what we're going to look at here is we're going to look at the frequency that these two things are orbiting each other as a function of time before they collide. So it's going to be a handful of seconds. You're going to see some bright colors that shows you the frequency, but then we're also going to listen to it too, where it's been shifted so that it's an audible signal, right? So they don't actually make noise. Well, they may make noise, but there's no air and space. They don't actually make noise, but they are orbiting each other with some frequency. So let's listen to that. So you can start to track the line here if you can see it. It's going to get brighter for those back in the cheap seats. See, they're spiraling into each other. Okay. So now we're like 5 seconds before they're actually going to merge, and you see now it's going to go crazy, and they're really rapidly running away. Okay. So that's kind of cool. Now, what's even more neat is at the end, there's this funny thing called a chirp. In this particular movie, which I encourage you to look up on YouTube later if you want, they're not focusing on the chirp, but what we can do is look at black holes merging, okay? So this is one of the exciting things we can do now that gravitational waves are an observable thing. So what we're going to look at is, again, frequency versus time, but this is over a very short time. We're just looking at the end when these things merge, okay? So they're spiraling in at this point. And we're first going to listen to it at the actual frequency, which probably no one older than me or even my age will be able to hear. And then we're going to listen to it shifted a couple octaves. Okay, so this is kind of fun. So that's kind of cute. That is what these black holes merging sound like. Okay, so when these funny cosmic events happen, it turns out these kinds of things this is how the elements are made. Okay? And so everything around you, everything that you're made of, was processed in a star at one point or another, which I think is pretty spectacular. So all of us in here are made of stardust. So is the table, so is the dirt on the ground. At one point, it was all processed in a star. So what we're looking at here is, again, our friend, the periodic table. But what we have is now the color code tells you just where it was made. So some of this stuff, only the hydrogen and the helium was made at the very beginning of time. A lot of it, though, was made in just stars like our sun. And then a good amount of it, more than half of it actually, was made in stuff like neutron star mergers, these big colliding things. Okay? So if you take a look at the Earth and everything you're made of, it basically comes from stars and from stellar explosions. So what could have happened several billion years ago, two neutron stars could have merged, right? When they did, they would release a bunch of gas. Eventually, that gas will coalesce and wind up forming our solar system. And then at some point, you come along, right? So you're made of stardust, and I think that's pretty amazing. Okay. So at this point, you might say, Zach, sweet, but what does nuclear physics have to do with any of this? All right. So we talked about these things merging and exploding, but why do we care about the nuclear physics involved? Well, what I have here is a model that you guys are going to get to run, or a few people are going to get to run here in a moment. And it's for a different type of stellar explosion. It doesn't matter the details of what it is, but what is important is that the output of our model calculation, and this is actually a real calculation, is we have brightness, so it emits some light as a function of time. So this particular stellar explosion gets really bright in a few seconds, and then over a minute or two, it dims down. Okay? And our model looks something like this, right? It's a magic box with a bunch of knobs on it. And of course, it doesn't really look like this, but it's close enough. Magic box, bunch of knobs on it. And for the knobs correspond to a lot of different things. But one thing that they correspond to is we have a knob for each reaction rate. So there are a lot of nuclear reaction rates that feed into this calculation. And what that is, in simple terms, is it's when I take one nucleus and I take another nucleus and I smash them together, what's the probability that they form something else? That is a reaction rate in its essence. And we measure that in Edwards' lab, as I'll mention. But that's what goes into these calculations. We need to know when I take two nuclei and I smash them together, what do I make? How often do I make it? Okay. So we can take our model. Let's just take one of our knobs, and let's crank that knob up. You see it change a little bit, and up. And we can keep cranking it up until finally we can see that depending on where we have this one knob fixed, in this case, this really changes the output of our model calculation quite a bit. Okay. And that is a really stupid problem to have because in the universe, there is one value for this particular nuclear reaction rate. If I take two atomic nuclei, two centers of atoms, and I collide them together, there's some probability they're going to interact. That's just that. But we oftentimes don't know what that is. Okay, so what we have to do is use these models to figure out which of these probabilities, these interaction probabilities, do we care about so that we can then go measure them, for instance, over at the Edwards lab, just about 100 yards from here. Okay, so I'm going to need a few volunteers here in a moment because this is important to remember, though there are a lot of nuclei in these explosions and a lot of possible interactions that can happen, just because something can happen doesn't mean that it will, and it doesn't mean that it actually matters or makes a difference. Okay? So the game that we're going to play here is called The Rate Variation is Right. So I'm going to need 4 contestants to come up here, and they are going to have to guess, they're going to have to pick of one of 4 reaction rates, will it matter or not? Okay, we weren't able to get Drew Carey here, but I'm from Northeastern Ohio, so this is as close as we're going to get for this. So can I get 4 contestants, please? 4 volunteers. Don't be shy. No? Okay, yeah, sure. Come on up, sir. I need 3 more for this to work. Nobody? You want to come on up? Okay, great. Great. Cool. Okay. So 2 more people. Can we get 2 more people? Okay. Oh, we got Rox going to come up? Okay, great, great. Okay, great. So what we're going to do, this is a really simple game. I wanted to give out gold, maybe when I'm tenured, but for now, what we're going to give out is the next best thing. It is chocolate. So we have Reese's Cups. Exactly. And so what we're going to do is I'm going to pick on you one at a time, and you're going to pick either rate 1, 2, 3, or 4. You have a cheat sheet that will not help you to tell you what this rate is, and you have to pick one that you think is going to make a big difference. If it makes a big difference, you get 3 pieces of chocolate. If it doesn't, I'll give you 1, because why not? I got a lot of candy here. Okay, so Rox, do you want to go first? Which one's going to matter?
I'll take number 1.
Okay, number 1. All right, so we're going to run our model calculation. This is an actual calculation, and we're going to see, does it matter or not? Okay, so it's running, calculation's running. Okay, and boom, 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 boom. Wow, it doesn't matter. Okay, sorry, there you go. You get 1 piece of chocolate. Okay, so let's go back to our modeler. Okay, so we know one's out, so we'll just go down the line.
I'm going to do 3.
You're going to do 3. Okay, feeling lucky. All right, let's go with rate number 3. Okay, we're going to run our calculation. It's running. This is me pounding on the computer because it's not running fast enough. Okay, and woo! Big money. All right, there you go. So you get 3 pieces of gold or chocolate. Okay, so that one, wow, that made a huge difference, right? Okay, so now 1 and 3 are out. So 2. Okay, we're going to see if 2 matters. Let's check. Let's run our calculation. Okay, it's running. Going to the coffee shop while it's running. And woo! That one's huge. This is actually the most important one for this particular calculation. So there you go. You got a future in this. Okay, so now, unfortunately, you don't really get a choice. You're just a contestant. So you're going to pick number 4. Wow, great. Okay, you're a good sport. Thank you. Okay, so our calculation's going to run. We're going to go run to the printer to get the results. And it has a marginal impact. Not really that important. But you were a good sport, so I'll give you 3 anyways. Yeah. All right, so thank you for playing The Rate Variation is Right. Okay, so you may wonder, well, wait a second. So is this really what you do? You just have all these different nuclear reactions, these nuclei and some probability for them interacting. You run your calculation and see if they matter or not. Yes, that is exactly what we do. So we don't really know a priori whether certain nuclei, atomic nuclei, are going to be important or not. It's not totally true. We can make some educated guesses. But in the end, it's really hard to tell if some nucleus it interacting with another one is going to be important or it isn't. So we just have to run our calculations and see if it makes a difference or not. Okay, but at least now all of you know that there are cool things happening in space, and nuclear reactions are related to these cool things in space. Okay, so cool. Now how do we actually measure these? We know what matters, what we need to measure, so how do we do it? Well, what we want to do is a nuclear reaction is basically this. Okay, we have some nucleus, so this atomic nucleus, in case we're not on the same page, has some number of protons at the center, has some number of neutrons at the center. Okay, and then what we want to see is how often does it interact with some other nucleus and make some other stuff. Okay, so we call one of these guys the target. That's the stationary thing that we smash stuff on. We call one of them the beam. That's the projectile that we smash into the target. And then these stuff, we call a lot of different things, but the reaction products work enough, and we need to place our detector so that it will detect these reaction products. Okay, so in a nutshell, that's all we're trying to accomplish over at the Edwards lab, is we run our model calculations to see what we want to measure, and then we say, okay, now we got to go out and measure it. Okay, so what we're going to do now is look at different reaction probabilities. Okay, so I'm going to need, at first at least, let's get 2 volunteers to run our local accelerator. Okay, this is a model of our particle accelerator. Okay, so we got 1 volunteer. Come on up.
Sounds like lots of fun.
Yeah, so we can do 1 volunteer at a time. This will be fine.
Does this have anything to do with string theory?
It's not really related to string theory, no. Yeah, yeah. Yeah, sorry, do interrupt me if you have any questions. Okay, so, yeah, sorry.
Take a step back.
Yep.
Given these diagrams, what does your 1, 2, 3, and 4 represent?
Given these, okay, so the question was, given these diagrams, what does 1, 2, 3, and 4 represent? What these represent are different nuclear reactions that can happen in our stellar explosion. So for instance, I have 6 protons and 6 neutrons, and I want to know how often does that interact with a nucleus that has 2 protons and 2 neutrons. I want to see how often do these 2 things fuse together, and that corresponds to that one down here.
So it represents different combinations of target and beam?
Exactly, different combinations of target and beam. And in your actual explosion, your stellar explosion, you just have a lot of these targets and beams, if you want to call them, floating around. And because it's so hot, they smack into each other. So, yeah, okay. Thank you for that question.
When you use your cyclotron, is it absolute 0 and in a vacuum when you do the smashing?
All right, so the question is, when we use our cyclotron, is it at absolute 0 and in a vacuum? We don't use a cyclotron over at the Edwards Accelerator Lab. I'll talk about the accelerator a little bit. There is a lab up at Michigan State University in East Lansing that I do use, and that has a cyclotron, and it's not at absolute zero. It is in a vacuum. It is extremely cold. It's at 4 Kelvin. In case people aren't familiar with that, the room is like 300 Kelvin, so it's super ridiculously cold. It's as close to absolute zero as we're ever going to get. Okay, so what we're going to do is take a look at how we make different reactions happen with our accelerator. So what I'm going to have you do is you're going to be the accelerator operator.
Okay.
You're going to take
Do I have
this.
to have a license?
You normally would have to have training, but for this, we'll waive it. I talked to the radiation safety officer. You're clear. No training required. Okay. So what you're going to do is take this nucleus. This is our beam. You're going to put it in the end here. This is our gravitationally powered accelerator.
Okay.
It's going to smash into our target, and we're going to see what we made.
Okay.
And then we're going to do that a few times, and each time we're going to tally what it is that we made on here.
Start here?
So start on that one. Yeah, we'll run that a few times.
Now?
Yep. Okay, so nothing happened, right?
All right.
So great. So then we can count this up, and I can tell you already there's 6 protons and 6 neutrons. So we're going to count the red. The red ones are going to be protons. The blue ones are going to be neutrons. And I'm going to forget that. So I'll write that cheat sheet for myself. Okay, in this case, it's easy. We count over to 6 neutrons. We count up to 6 protons, and we made one there. Okay, so now let's do that again.
Is that a new particle?
In this case, nothing happened. That's called scattering. You just scattered it right off.
Up here?
Let's do this one again. We're going to run it 4 times and to get some statistics, right? This is what we got to do. So go ahead.
1 of one.
Yeah. Woo, okay. So this time we lost 2 blue guys, and the blue, according to my cheat sheet, are neutrons. So we still have all 6 of our protons. So we made one of these, okay? So now we'll have you run this up at the higher energy, okay?
Right here?
So yeah, we're going to increase the energy, all right? Woo! Now, amazingly, you only actually lost 1 neutron. Okay, so we only lost 1, so now we're up here, okay? And I should do that one in a different color, because otherwise, how will I know which was which? There we go, okay. So let's pick a different nucleus here, because they're already pre-made. So go with the high energy one again.
This one?
Yep. Oh my goodness. Oh, we forgot to put the target, you know. I swear I'm an experimentalist. Maybe I've been running too many model calculations lately. That's the problem. Okay, let's actually do this the right way. That's good that nothing happened. That would have been pretty amazing had something happened.
All right. You mean because of what we dropped it?
Yeah.
Are you arranging those protons and neutrons in the same way around that target?
No, I should do that. Yeah, exactly. So let's go with the high energy one more time. Woo! And in this case, wow, amazingly, again, you really only knocked off 1. Okay, so we're going to tally that up. The data are what they are. Okay, so we got 2 there. So thank you. If you like candy, you can go back to your chair. Thank
In
you.
real life, how many ends would you really do from, say, each height to feel comfortable that the data that you gathered was valid?
Right, so the question is how many ends do we do from each height to be sure that the data is valid? It really depends on the thing that we're looking for. So oftentimes we would like to, for the reaction products, oftentimes we'd like to have thousands of these, so we'd like to see at least thousands. Now sometimes when people are trying to make new elements, new chemical elements, so like add a box on the periodic table, they'll run for months and months and months, and they'll get a few. And you'd like more, but you can't get it, so that has to be good enough in that case. So it depends. Oftentimes, it's actually millions of these collisions per second that is happening.
How
Yeah.
long do these newly created particles last?
Yeah, so the question is, how long do these newly created particles last? It can depend. So some last for millions of years. Some last for seconds. Most last for milliseconds. So just, that's it, then they're done. Then what happens is they undergo a decay. So one of the neutrons in the nucleus turns into a proton, or the other way around. And that happens repeatedly until you get something that lives forever. So, yeah. All right. So we need 1 more operator for our accelerator. Do we have somebody who's really tall? That would be good. Not to put you on the spot here, but I need someone who's taller than me. We could do a chair. I'd rather not do that. Let's see, do we have somebody? Hey, Carl, we got Carl back there. He's a licensed accelerator operator. Okay, got a real live person. Okay. Yeah, sure.
Does the result change depending on the position of
The target?
target?
So yeah, the question was, does the result change depending on the position of the target? The answer to that is kind of yes, but in a really tricky way. Okay, so in real life, we have a piece of target. It looks like kitchen aluminum foil, and our beam goes into that. And the position there doesn't matter so much. But what's going on a quantum mechanical level is you have one nucleus that's coming in and colliding with another. And technically speaking, how close that nucleus comes to the other, that affects what reaction happens. Now, how we determine how close it came is a little bit tricky. What we have to do is measure, keep going back and forth here, we have to measure the angle and the energy of the thing we produced, and then we can work backwards to say how close these two things were, which is kind of amazing. We just talked about that in my grad nuclear physics the other day, actually. Okay. Right, so what we're going to do now is see what happens when we up the energy of our accelerator. So if our operator could use the upper one here. Bam. Okay, so that made a huge mess. So what we produced here, pull the green guys off because I'm not going to count them. So we have a single proton, right? Protons are red. And we have 5 neutrons. Okay, so we're now down here, and I ran out of colors, so I'll have to hash that. Okay. So if our operator could kindly run, let's just do one more. Yeah, do you want to pick another one, Carl? Thanks. Okay, so go ahead and do the top one again. I swear I'm an experimentalist. See, this is why my grad students are so important. They really keep things going. Okay, thanks, Carl. Woo! Okay. So that stuff was close to it, but it wasn't really on there. This really made a mess. So what we have, if I pluck this apart, is we now have 3 protons, and again we have 5 neutrons. So thanks, Carl. Okay, so 3 protons and 5 neutrons. So we're here. Okay, and so what did we see is that depending on how our experiment is set up, we can make really different stuff. Okay, the nuclear reactions that we're going to measure, it really depends on how we tune our accelerator. So how much energy we give the beam. It could have mattered where I put the target if I put it, in this case, further to the side or right in front of it. And so experimentally, that can be one of the challenges, is deciding how do I set this stuff up so that I can actually measure what it is I'm trying to measure. Okay, so that's a example of experimental stuff. Okay, so all right, so we know cool stuff's happening in space. We know that nuclear physics is somehow related. We know how to tell which nuclear reactions we care about, and we know how to measure them if we can produce a beam, right? So how do we actually produce the beam? Okay, so how we do it just 100 yards from here at the Edwards Accelerator Lab is using a device that's not unlike this thingamajig here, except about 10 feet tall. Okay. So can anyone tell me what this thing is? You've probably seen him before. It's making his hair stand up. It's a Van de Graaff generator, all right? Exactly. So what this Van de Graaff generator is what you have here is there's a belt rotating inside really rapidly, I don't know, tens of miles an hour, okay? It's scraping at the bottom off the slide here where you can't see. It's scraping a thing up at the top. And what it's doing is it's stealing electrons from stuff here on the bottom, and it's donating them up to the top. And it's doing that over and over again. And as you deposit these electrons here, this thing becomes electrically charged. And what it does is when he puts his hand on this Van de Graaff generator, that charge gets donated to him. It gets donated to his hair strands. They now all have the same electric charge, and like charges repel. If you don't remember that from your intro physics, that's true. Okay, so that's what's happening. And we do that at the Edwards Accelerator Lab with something that is about 10 feet tall and maybe a foot or so wide. And this is a mini one here that after the discussion you guys can come play with. So this is kind of how it works. So I have a mini Van de Graaff generator in here. I'm going to press a button. It's going to make a belt go. And this thing here, this mylar foil, is going to get charged. Okay, and it's a magic show, right? Woo! And so you see, you can use these electric potentials to accelerate stuff away from you. Okay, so that's what we do, is we have one of these that's about 10 feet tall. It's in the tank the size of a school bus. And we can get it charged to a really high charge. And what it winds up doing is attracting atoms that have an extra electron, and it repels ones that are missing some electrons. Okay, so
Could you use that for propulsion?
so the question is, could we use this for propulsion? You, in principle, if you're brave enough, could sit on some charged rail car and get repelled. Well, the thing is, it works. You need some. So the question is, would it work in space? And you need something to be repelled from, right? So it would get pretty scary. You need a pretty high voltage, because the further away you get, it's going to repel you less and less. Yeah. Okay, so that is our Van de Graaff generator. I do encourage you to come up and play with that afterwards. Okay. So the actual lab here, I just wanted you to see it. If you've never been to the accelerator lab, please come by. You can contact me. You can contact our lab director, Carl Bruni, and you should come check it out, because it's a pretty neat place. It's over just north of the Clippinger parking lot, north of Meredith Park, and we have a lab that's built into and next to the hill there, a little bit south of the library. So what we have is our accelerator is that big orange tank there. It's about the size of a school bus, and we have one of these Van de Graaff generators, but it's like 10 feet tall and a few feet wide. And then we can produce our beams there, we can set up our targets, and then finally we can measure whatever it is that we produced using our detector systems. Okay, so this is an example of a detector, and that is the last thing that I'll talk about here. So how do we detect the reaction products? Because we're almost done with this sort of scheme of logic here. We know cool stuff happens in space. We know nuclei are involved. We know how to tell which nuclei are important. We know how to produce the beam and how to set up this reaction. And the final thing is we need to measure what it made. And so we use a radiation detector. Okay? And what these radiation detectors are, they're a lot of different things. But what basically happens is whatever thing you produce in the reaction, whatever it is, it comes in and it interacts with this thing. And it usually winds up creating an electric current. And how it does it, there's a lot of different ways, so we can talk about it if you're curious. Winds up producing some electric current, typically, and we just measure that. And if you'd like to play with one afterwards, I have a Geiger counter here that only the people in the front can see. And what we can do is we can look at this Geiger counter, and you'll see that typically we're not producing a whole lot, or we're not detecting a whole lot. Okay, this is the actual detector here. But for those people who can see, what happens when I take something that's radioactive, this is a lantern mantle that has thorium in it, it turns out. I can put that on my detector, and you see a peg, right? And it's okay. It may seem scary that it pegs. This is not that much radiation. Okay, it's not really a big deal. So, what's that? This one doesn't have a sound, no. So the question was, does it have sound? We do have one that's a so-called chirper at the lab. The battery died, and Don and I couldn't get it going before it came here. So I planned on having that. Unfortunately, it doesn't have sound. That would be really cool. But what I encourage you to do is come up here later, and what you'll see is we can take this lantern mantle with the thorium, put it on the detector, and it'll peg. In case you're curious, is there just something funny about the plastic? We have another lantern mantle here that doesn't have thorium, and nothing happens. And then also, if you come up here later, you can see that occasionally you'll get a count anyways, okay? And the reason is not because this thing doesn't work. It's because the world is actually radioactive, okay? So that's one complication with our experiments, is that we know what we want to measure. We produce these reaction products, and we want to measure them, but it turns out similar things are made all the time, okay? So the world is actually extremely radioactive. If you come to the open house, you'll get to see a cloud chamber being operated. And what this is, it's a supersaturated gas of alcohol. That doesn't matter. What matters is that when a charged particle goes through it, it leaves a funny track, like there's kind of an alcohol mist, and it leaves a little cloud behind it, okay? And this one is sped up here. I know there's some radon gas in there. But what you would see if you don't have any, radioactive source, like a special lantern mantle by there, you'd still see a few every second going through here, okay? So there's radiation from space going through your body a few times every second, and there's nothing you can do about it, all right? You can go underground, but then you'll actually find that there's rock underground, right? And rock is extremely radioactive, okay? There's a lot of uranium sitting around, there's a lot of thorium, there's radon gas, and that's all over the place, and that's undergoing radioactive decay. And you'll say, okay, I got you beat. So if I have to go underground, but I can't be near rock, how about I go deep sea? Let's go in a submarine. All right, almost, but you are radioactive, okay? So you have a lot of different radioactive nuclei in your body, but one example is the potassium in your body. So if you guys know much about how your nervous system works and how neurons fire, it turns out potassium is key to that process. And a decent amount of that potassium is made of this isotope called potassium-40. So it has 19 protons, which makes it potassium, and it then has 21 neutrons. That part doesn't matter. What does matter is that it undergoes radioactive decay. And so you have radioactivity actually in you all the time, and that's just fine. And then it's experimentally challenging though. One fun fact is actually, it's a really good thing that the world's so radioactive, because otherwise we wouldn't be here. So the Earth would be a cold rock floating in space with no life on it probably, if it weren't for the fact that the Earth is so radioactive. So actually, the reason it's not a molten solid rock, or the reason it's molten in the core and not a solid rock, is because there's still radioactive decay going on there, and that's actually a good thing. Okay, so with this, I'm going to try to conclude, and we can just do Q&A here. But you guys can't see the cartoon; you'll see it later. But in any case, what I hope that I communicated to you guys is that nuclear physics is really important for understanding the universe. Hopefully you understand roughly how we identify what we want to measure, how we actually measure it, and all of that jazz. And if you don't, we should elucidate that in the Q&A. And then finally, I want to leave you with the Carl Sagan gem that we are star stuff. So, thanks. Okay, I should take questions now.
Questions?
In the back. Yeah. Oh, sorry.
Could you actually talk a little bit more about how that electric current is induced in that cathode ray?
So the question was, can you describe a little bit more how that electric current is produced? So are you talking about in this detector here? So in this particular case, what's happening, this is a Geiger counter. What we have here is basically a tube of gas. It's the same thing that's right here, so you can look at it later. We have a tube of gas, and inside here we have a wire that's charged to a really high voltage. So what happens when a charged particle goes through gas, it can interact with the electrons on the atoms, okay? And it can momentarily free those electrons from the atoms, from atoms in there, okay? It's doing that as it's traveling through. And normally, they would just recombine with the atom, nothing special would happen. But because this is a charge to a very high voltage, once I've freed an electron, if I put it at a positive voltage, the electrons will get attracted and sucked into that. And if you have a bunch of electrons streaming into a wire, that creates an electric current. So that's how that one works. That's how a lot of the detectors work. Yeah, Carl.
Do you guys ever have an open house?
Oh, the question is, do you guys ever have an open house?
We announced that.
So we do have the, just in case anyone wasn't aware here at the beginning, the Physics and Astronomy Open House is this Saturday from 10 to 4, unless someone should yell at me, 10 to 4. We'll have fun stuff in Clippinger, but there will be tours going on the whole day in the Edwards Accelerator Lab. So, yeah, question.
So let's make some gold.
Okay.
So you know the target, you know the beam, the energy, so
Yeah, so the
you're going out there and make something.
So the question is, or the comment is, let's go make some gold, right? Why don't we just go make gold? We could totally do that. The problem is, it's small amounts and it would cost a lot more than it was worth. one fun fact, this is kind of amazing. So there's a paper that is a preprint that's out. It's not published yet, but from that neutron star merger that I showed you guys earlier, does anyone want to guess how much gold was made in that neutron star merger? Quantity, just a rough order of magnitude. Was it a ton? A ton? We have a ton. Okay. Okay. Price is Right rules. Closest without going over. Okay. No kidding. A gram. Okay. So we have a gram. We have a ton. Okay. We have one more guess. Let's take someone who has a chance. Song. What do you think? What's that? More than the size of the Earth. And this guy, he's cheating. He's a nuclear astrophysicist. He's correct. It's between 15 to 70 Earth masses of gold were made in that one collision. Isn't that amazing? Well, it's unfortunately several million years away if you were traveling at the speed of light. So, yeah, all you have to do is design a spaceship and live for another couple million years, and you can go out there and get it. So the question is it a clump? It's dispersed over a relatively large distance, but it is plausible that a lot of that could condense later on, but could coalesce. So what typically happens, we believe, is that you have one of these sort of merger events happen. That gas floats into space undisturbed for a very long time. Maybe another one will happen, maybe another one, maybe some other stuff will happen. And eventually, by pure happenstance, gas that is mixed into all the other gas will wind up coalescing to form our solar system. And you might say, well, wait a second, then why don't we have like actual gold planets floating around? It's because it's mixed in with all this other stuff. Yeah, so, yep.
A question about your periodic chart.
Yeah.
You had at the very bottom man-made elements.
Oh, yeah, so I was cheating a little bit. Yeah, they're not all made in stars.
That's okay, but I was thinking that you stopped your supernova synthesizer somewhat before, let's say, AM, American.
Americium,
Why
yeah.
did you stop there? Why don't you believe that in these supernova, these neutron collisions, that heavier elements aren't made? Why isn't the universe full of exotic elements that you theorists could detect? I realize the lifetimes are very short.
Yeah.
But why not speculate that elements do exist
So,
after these collisions?
right, so the question is, why don't we speculate that certain elements, even more exotic ones, exist in these collisions? And we do, to some extent, put elements that are not on this chart in our calculations, but we use nuclear theory estimates to estimate their properties, and typically speaking, you just wouldn't really make any of them. Or if you would made them, they would immediately fall apart. And immediately, in my terms, means like a femtosecond. I don't know if that means anything to anybody here, but imagine a decimal point and then 15 zeros and then a 1 seconds. So, yeah, so they don't exist. Right, and then as far as how we decide, well, which one of these elements were made in small stars, which one were made in supernovae, this comes from our astrophysics model calculations, and this one's actually out of date. So if I wanted to go with the latest and greatest, what we've learned in the past decade is that our supernova would actually end somewhere around zinc, somewhere in this zinc to tin region. It would end somewhere here. And when my student Kristen Brandenburg gets her PhD in a few years, she'll tell you, she's in the back, she'll tell you whether it ends between zinc and tin. That's what we're working on. The neutron star mergers, though, we believe that actually makes most of the rest of this heavy stuff. Yeah. So, yep. Gene.
Why is gold so valuable for jewelry?
Oh, yeah. So why is gold so valuable for jewelry? Well, I have my own sociological answer that involves a little bit of nuclear physics. So, whoops. Yeah, there we go. Okay. Where's my chart? So you see, it comes down, I think, to this. There's a few things. People like shiny things. Gold is shiny. That's good. You need to have it not be so popular or so abundant that it's really easy to get, like iron. But the man's got to make money. You know, whoever's making the jewelry, right? K Jewelers has to make money. And so you need it to be abundant enough, right? So that's, I think, why. I mean, you could, for instance, try to make jewelry out of rhenium. It's probably shiny as well, but you probably go out of business pretty quick because you run out of rhenium. That's my guess, yeah. Question?
I wanted to ask about this chart because I'm surprised at the relative size of gold to iron. It's a bigger percentage than I would have thought.
Yeah, so the
You can't tell really, but it looks like
right.
fifth, sixth.
Yeah, so the question is, why is the gold so similar in area to iron here? You'd think it would be a lot less. There are a couple reasons. So one is it's pretty hard to judge actual numbers based on area. There's a great book by Edward Tufte called Visual Display of Quantitative Information, if you want to see that. But also, this is in the crust. And it turns out that most of the iron that's in the Earth is actually in the core. And so you can't dig that up. So if you plotted instead relative abundance for the whole Earth, the iron would be much bigger. If you plotted for the whole universe, the whole chart would just be that hydrogen box, pretty much. You'd just see hydrogen and helium, and everything else would be really tiny. So that's why I like this one, is it kind of gets the point across, but you can still read it. Yeah. Sorry. Yeah.
What scientific purposes does helium have, and what do you do for that? Is it really running out?
Yeah, so the question is that is the helium that we have really running out, and what scientific purposes do we have for it? So the answer to the helium running out, there is a helium shortage. So it turns out that helium, if you just have your party balloon of helium and you pop it, that helium eventually will escape the Earth. All of it will just sort of float away. So you're going to say, wait a second, well then where did they get that helium? You know, they didn't go out in a spaceship, right? It turns out it's from radioactive decay from rock in the Earth. So when you have uranium, for instance, a lot of times it'll emit a so-called alpha particle. So that's 2 protons and 2 neutrons. And once you add some electrons to that, that's just helium. And so that's where the helium is actually coming from. And so we can get helium from just putting a pipe near a bunch of rock down in the Earth, or you can get it from, where most of it is from right now is natural gas, shale gas. You can't really create it. I mean, you could create helium, but it wouldn't be worth the money. So you just kind of have to wait and capture it. Now, so there is somewhat of a shortage. It's not super dire yet. As far as what we use it for, there are a lot of different things. So helium can be really useful in some of our detectors. It turns out when you take helium and you remove one of the neutrons, you have this thing we call helium-3. It turns out it really likes to capture an extra neutron, really likes to. And so if you want to detect neutrons, it's very useful to fill a tube with a bunch of helium-3. Now, one issue is it's extremely expensive, so it's hard to get, but we use it for that. Also, the helium nuclei, if we want to create a beam of helium, what we actually do is we take a gas bottle of helium, we leak it into this thing called an ion source. It's a little bit magic, but what it does is we can donate an electron to it to make it charged, and then use that, accelerate it with our accelerator, and it's the beam now. And we do that with regular helium, and then our friend, the helium-3 as well.
So what are blimps filled with?
What are blimps filled with? I think a blimp is filled with helium, is it not? I don't know much about blimps. I'm not an engineer. Yeah, not necessarily hydrogen. I mean, it could be hydrogen, actually. An interesting thing about hydrogen, as long as you don't mix it with oxygen, it's not actually explosive. You need to have about between 10 to 70%. Fun fact. And if you ignite it, it turns out it doesn't really typically explode if you're careful. So, yeah. Yeah, if you're careful.
Anybody else? All right, Ross. Last one.
What kind of reactions do you study? And tell us why you study those reactions. Why are they important? Why would we care?
So the question is, what kind of reactions do you study? Why are they important? Why do you care? There's a lot of answers to that question. I can tell you, just as an example, these reactions here, I put up here not by accident. I actually do study these particular reactions because I want to understand these particular explosions. Okay, so for instance, this one is a reaction that my student Doug Soltesz has sort of measured. We've measured it in a funny roundabout way, but he's measured that and we're analyzing it. I was just up at Michigan State. We were measuring that one. As you know, Carl has devoted a large part of his life to understanding that one and doing a great job. So, for instance, you may want to study them for stellar explosions. You may want to study them for medical isotope production. So when I was a postdoc at the University of Notre Dame, we were trying to figure out what the best way was to make technetium-99 metastable state. That doesn't matter exactly what it is, but it's really useful in imaging for tumors, for cancer. It's really useful to hook that Tech-99m to a sugar. You drink this nasty sugar concoction. The tumors eat everything faster than the regular cells, and they like to eat up the sugar. And then the Tech-99 gets concentrated there, and that winds up emitting a light particle, a photon, and you can detect that and tell where the tumors are and how much you have. And it turns out we don't know what the best way to produce that is. And so we worked on at Notre Dame, and it's almost finished, is what's the best way to produce Tech-99m. So there's a lot of different reasons, but those are two examples. Yeah.
Okay, so shall we thank